On the moon, an astronaut tosses a baseball from a height of 64 feet with initial velocity of 23.6 feet per second. The formula for the vertical motion of an object on the moon is h of t equals negative 2.67 t squared plus v times t plus s, where v is the initial velocity and s is the initial height. Again, t represents the time in seconds, and h is the height above the surface of the moon. What we want to do is write an equation that models the situation. So, do we know the value for v, and do we know the value for s? V is the initial velocity, and they said it's going to be 23.6 feet. So that is going to have to get substituted here for v. Now for s, talking about the initial height, we see how the baseball is being tossed from a height of 64 feet, so that's going to get substituted in here. So our function should look like this. h of t equals negative 2.67 t squared plus 23.6 t plus 64. Our next question is, how long will it take for another astronaut to catch the ball at a height of 6 feet? So if we think about height of 6 feet, what part of our function is that? Is that an input or an output? The height is an output, right? h of t. So I have an output of 6 feet. So if I substitute that into my function, what could I do? Well, I have to find its corresponding input. So graphically, I could solve for t, right? The time when that happens. So this would go in my y1 of my calculator, and this would go in my y2, and I would have to work on adjusting the window. Again, Desmos folks, this is your first function, this is your second function. Remember, as you're typing them in, the calculator recognizes x as the variable for the input, so you're going to have to substitute an x in place of t. So we would have the screen of our calculator look like this. Now we're going to have to fix the window, like we said, and Desmos folks, you're going to click on the wrench and adjust our values accordingly. So what would be some good values to look at? Well, we want to see when it's getting a height of 6 feet, so that's going to help us adjust the y's, the outputs, and then we're going to think about time that it's going to happen. And notice that things move more slowly on the moon because the gravity is different there. So what I'm going to do for my time is I want to see what's happening at 0. So I'm just going to set it from -5 to 25 seconds, counting by 5 seconds. I can always adjust if I need to see more or less of a certain part of my graph. The heights, again, I'm not sure how high it's going to go, so I'm going to estimate a maximum of 150. And I do want to see when it would hit the ground, perhaps, or the surface of the moon. So I went from -10 to 150, counting by tens. So I'm going to adjust my window to match those items. And you guys can adjust Desmos with the wrench. Again, x is greater than this, but less than that. There's your step. Y is greater than this, but less than that, and there's your step. Once you have your window set, if you hit graph, you again double checking to see, do you see everything that you need to. So here is the path of the baseball being thrown by the astronaut, right? So that's where it's being released from, going up, and we want to see where it's going to be caught 6 feet above the ground, and so that would be this location here. So we're looking for this intersection point. Again, graphing calculator folks, you press second trace, option 5 intersect. And it's going to ask you for the first curve, press enter. Second curve, press enter again. We don't want to guess, press enter a third time, and we see our intersection point. Desmos folks, you can click on that intersection point and you should get the same values. So about how long is it going to take? We can do some rounding here and say about 10.8 seconds it will take for the other astronaut to catch the ball. If you went to the nearest hundredth and said 10.84, that's fine as well. You have your evidence. Again, just say about to talk about the rounding, and you are good to go. Again, evidence on your paper, you've got the steps. You've got the coordinates and you have your summary sentence. You're always welcome to insert pictures of your graphical evidence as well, or do a quick sketch with some labeling to show how you're arriving at your results. You can also use the microphone feature and talk through the explanation as to how you're arriving at your results as well. But the key things, again, is the model, what you're using to help you solve, all your supporting evidence, and a summary sentence.